Good morning, everyone. My name is Daniel John. Today, I'll be presenting my individual project, a network intrusion detection system, or NIDS, built entirely in Python. The system monitors live network traffic in real time and automatically raises alerts when it detects suspicious behavior, specifically port scanning and high volume traffic floods. This presentation will also end with a live demonstration of my system running. This project has three objectives. First, to capture and monitor live network packets in real time using SCAPI library on a Windows machine. Second, to automatically detect two types of suspicious activities. They are port scanning, where an attacker probes many ports to find open services, and high traffic flooding, where a single IP sends an abnormal volume of packets. Third, to present all of this through graphical user interface GUI built with Tkinter so users can see what's happening on their network without needing to read raw packet data. This system follows a five-stage pipeline. Network traffic enters from the interface, and SCAPI sniffs functions function captures every IP packet. The packet callback then extracts the IP layer, pulling out the source IP, destination IP, protocol type, and destination port for TCP packets. This data feeds in to the detection engine, which maintains two counters per IP address using Python defaulting, one for total packet count and one for unique TCP destination ports. If either counter crosses its threshold, an alert is generated and displayed in the GUI. One important design decision here is the packet sniffer runs in the background daemon thread. This keeps the Tkinter GUI fully responsive. Even during heavy traffic bursts, the interface never freezes. The system implements two detection rules. The first is port scan detection. If a single source IP accesses more than 10 unique TCP destination ports, the system classifies this as suspicious and generates the alert. Possible port scan detected from the IP. This works because attackers typically probe dozens of ports when mapping a target. Normal users don't do that. The second rule is high traffic detection. If one IP sends more than 150 packets during a monitoring session, the alert fires. High traffic detected from IP. This catches flooding behavior that could indicate a denial of service DOS attempt. Both rules use efficient in-memory data structures that set for unique port counting give O1 lookups. And once an IP triggers an alert, it is added to the alerted IPS set, so the same IP won't flood the log with repeated alerts during the same session. Now, I would like to switch to the live system and walk through four steps. First, Here you can see the idle state. All counters are at zero. All counters here are at zero. Packet captures is at zero. Alert detected is at zero. Most active is at none. And, and the traffic status shows none. Now I'll click start monitoring here. You can see packets starting to populate the log area in real time. Each entry shows the protocol source IP, destination IP, and port numbers for TCP packets. I now generate a high traffic to trigger an alert. Watch the packet counter climb, and there, once it crosses 150 packets from the same IP, you can see the traffic status to suspicious. An alert message appears in the log. Alert. Follow the timestamp and offending IP address. The alert detected counter is incremented to 1. Here you can see the alert was written in the persistent to this, with full timestamp, alert time, and IP address. So even after the session ends, there's a record for forensic review. The results confirm that all 3 objectives were met. The GUI launched correctly. Real-time monitoring worked as expected, and the detection engine successfully raised an alert at 308 packets, well above the 150 packet threshold. The system correctly distinguished normal traffic from suspicious traffic, and all alerts were written to log.txt with accurate timestamp. One limitation I noted is that SCAPI sniff function captures all network interface by default. In a production environment, you would specify a particular interface to reduce noise and irrelevant traffic. In conclusion, I successfully built a functional, rule-based network intrusion detection system in Python that achieves all 3 objectives: real-time monitoring, automated detection, and a graphical interface. For future work, I will look at adding brute force detection, integrating a database for historical log analysis, adding traffic visualization charts to the GUI, and eventually applying machine learning techniques to reduce false positives. Thank you for your time.